Now let's flip back to a musical example of this and how it applies in permutations. Well, you can do the exact same thing that you did with these two phrases of words with phrases of notes. Looking at each of these permutations, you'll notice that the density is 6. That's good because it shows you're in the same group. For the next two, we want to address each individual lem separately when scoring this pattern. When you look at the leading common string and the longest common substring of each of these patterns, you need to add up what's happening on each limb in order to get the total score. So we first look at the right hand on the ride symbol, and we see that it's not playing on each of these two patterns, or it's resting for 3 subdivisions of the note. Here you can give it a score of 3. We're playing nothing for both of the patterns. Now let's go to the left hand. The left hand is playing the second and the third note of the triplet on each of these patterns. Again, you rest on the first, you play on the second, you play on the third. That gets a score of 3. Now let's look at the right foot. The right foot's playing the bass drum, and it's playing the first and second notes of the triplet and resting on the third. That's common for both the phrases, and so again, you have a score of 3. Now finally we look at the hi-hat foot, your left foot. Now that's playing slightly different patterns on each of these permutations. On the first one, it's playing the first and the third beat and resting on the second. In the second permutation, it's playing the first and the second beat and resting on the third. These are obviously different. The similarity ends on the first note, and so we can only score this transition as a 1. When you add up the score for the leading common string and the longest common substring, you end up with a score of 10 for each. Now, as I mentioned before, there are times when you get scores where the leading common string and the longest common substring are the same. And this is an example. As I write this piece of music, I want to preference patterns that have better leading common strings than longest common substrings. And the reason for that is that you read a piece of music from start to finish, and you experience each individual note and each subdivision of that note linearly in one direction. Now, while referencing common pieces of music is great for repeat listens, if you're experiencing this for the first time, I want this to be unraveled in a meaningful way. And so with that, I focused on revealing these new permutations in a linear way. Now, I think one of the coolest things here is you don't have to use this method to arrange your permutations. You could put the least common permutations next to each other, or you could invent some entirely new mathematical way to lay these out. There are 4,096 to the 4,096 scores available to you, and I think you should try to explore some of them. To get back to the point, I want to preference the leading common string, and to do that, I multiply the result of that score by 10, so that it'll always be bigger than the result of the longest common substring. So now that the computer has a way to mathematically score each of these permutations, we need to search through the space and pick the score that's the best. And to do that, I used a technique called simulated annealing. Now, simulated annealing is a search technique you can use on really big problems that aren't necessarily defined by a mathematical function. One way to picture how simulated annealing works is to imagine that you've got a topographic map up on a wall. Let's say you wanted to figure out what the peak of that map was, but I wasn't going to let you look at the map. Let's say I blindfolded you and gave you darts and told you that every time you hit the map, I'll tell you the elevation of the point of impact. So you stand back away from the wall, you put on your blindfold, and you throw a dart at the dartboard. I read out an elevation, you repeat this process. And then we stop after a period of time, and I tell you, this dart over here, and I point you in the right direction, is where you hit the highest peak on the map. Now I give you the darts back, and I say, go ahead, throw again. Well, what you're going to want to do is you're going to want to aim for that area because that's, in your mind, is the highest point so far. And so, as you throw the darts at the map, you have a smaller circle where you're hitting, and maybe you find a point that's higher than the previous one. And so you aim for that. And then you throw your darts again, and you get a slightly higher peak. It may seem strange, but this technique actually works really well for looking through large data spaces that aren't defined by a constant function, much like our permutation set that we've set up. Now, how do we use this technique to arrange different patterns to form an overall piece of music? Well, let's just take all the patterns and shuffle them up randomly. Let's do that 10 times so that we have 10 different pieces of music. And now keep in mind, these are random. These are totally random. But what we can do is now run through each piece of music quickly and calculate the different score between each of the patterns. And once we have that, we can calculate the overall score for the piece of music. We'll now take each of those pieces of music and compare the scores. Which one of them is best? When you find that, take it and keep it. And then repeat the process again. But this time, start with that piece of music and move things around by slightly less than you did the first time. Score each of the pieces of music, pick the best one, and repeat. Each time reducing the randomness which you allow to creep into the system. As you move through this process over and over again, eventually you end up with a score that's maximized for the given constraints that you've given the computer. After we finish this process, we end up with a list of the different permutations, going from 1, which is resting on all limbs, to permutation 4096, where we're hitting each note of the triplet with each of our limbs. That's the final piece of music. After we have the list of the 4096 different patterns, we convert that back into kick drum, snare drum, ride cymbal, and hi-hat hits in zeros and ones. Then we run it through the LilyPond conversion software that we wrote to turn it into something that LilyPond can understand. Feeding this result into LilyPond, we get a PDF of the piece of music and a MIDI file of what it sounds like. And so that's it. I hope these videos have been helpful in showing you what went into the new composition Permutations. If you want more information, I've detailed the whole process in the album notes. I really hope that this piece of music helps you improve your four-way independence and opens up new windows in your playing. Thanks for watching.